Welcome to StatTrick's video tutorial on advanced placement statistics. In this lesson, we will work step by step through a regression example. Regression analysis is usually handled by a computer or by a hand calculator, and computations are hidden from view. In this lesson, though, we will work through a regression example by hand and show all of the computations. You will learn how to conduct a complete regression analysis, how to find the regression equation, how to compute the coefficient of determination, and how to use the regression equation to make predictions. Let's begin by describing regression notation. With simple linear regression, the raw data consists of two variables, an independent variable and a dependent variable. Capital X is the independent variable. Capital Y is the dependent variable. All of the other variables used in regression analysis are derived from X and Y. X bar is the mean of X, and Y bar is the mean of Y. Lowercase x is the deviation score for X, which is equal to X minus X bar. Similarly, lowercase y is the deviation score for Y. The derived scores are used in various formulas to compute regression outputs. B0 is the y-intercept in the regression equation. B1 is the slope of the regression equation. Y prime is the predicted value of y based on x. R sub xy is the correlation between variables x and y, and R squared is the coefficient of determination, a measure of how well y is explained by x. Now that we are familiar with regression notation, let's talk about regression analysis. With simple linear regression, the researcher begins with raw data, an independent variable x and a dependent variable y. He enters the data into a computer. The computer produces regression outputs. It defines regression coefficients for the regression equation, and it computes a correlation coefficient that defines the coefficient of determination. The computer does a lot of good work, but it is a black box. It hides the internal computations. In this lesson, we're going to show you what goes on inside the black box. You'll see how the computer uses the raw data to compute mean scores, deviation scores, and summation scores, and how they go into various formulas to produce all of the regression outputs. In short, you'll see the gory details of what it takes to conduct a regression analysis. In this section, we are going to complete by hand the initial computations that are normally handled by a computer. For our data, we will use a set of math scores and statistics grades. Column X shows the independent variable, math scores, and column Y shows the dependent variable, statistics grades. Here, capital X and capital Y are raw scores. You can tell from this table that the first student had a math score of 95 and a statistics grade of 85. The second student had a math score of 85 and a statistics grade of 95, and so on. One of the first things we will do with these data is to compute deviation scores, which are represented by lowercase letters. Then we'll compute the squares of the deviation scores, as well as the deviation score cross products. We'll also need to compute the sums of several columns. And the last row of the column will display the mean of the raw scores. Now, all we need to do is fill in the table. We begin by computing the sum of the raw scores. The sum of the X scores is 390, and the sum of the Y scores is 385. We will use these sums to find the mean of the raw scores. Since there are 5 x-scores, the mean of x is 390 divided by 5, or 78. And the mean of y is 385 divided by 5, or 77. Now that we have the means, we can compute the deviation scores. The deviation scores are equal to the raw score minus the mean. So the first deviation score for x is equal to 95 minus 78, or 17. The second deviation score is equal to 85 minus 78, or 7. The remaining x-scores are computed similarly. And the deviation scores for y are found by subtracting the mean of 77 from each of the raw scores. Then we find the square of the deviation scores. For variable x, 17 squared is 289, 7 squared is 49, and so on. We do the same for variable y. And then we compute the cross products of the deviation scores. 17 times 8 is 136. 7 times 18 is 126, etc. And finally, all that is left to do is to compute the sum of the last 3 columns. The sum of the x squared column is 730. The sum of y squared is 630. The sum of cross products is 470. Among all these numbers, 5 are especially important: the mean of x, the mean of y, the sum of x squared, the sum of y squared, and the sum of xy. These 5 numbers, shown in red, are the ones that we will use to complete our regression analysis. In this section, we use our initial computations to define the regression equation. The regression equation is a linear equation in the form y prime equals b0 plus b1 times x. Here, y prime is the predicted value of the dependent variable, and x is the raw score of the independent variable. To use this equation, we need to solve for b0 and b1. Let's begin with b1, which is equal to the sum of cross products divided by the sum of x squared, where x and y are deviation scores. From our initial computations, we know that the sum of xy is equal to 470, and the sum of x squared is equal to 730. Plugging these values into the equation, we see that b1 is equal to 470 divided by 730, or about 0.64. Once we know b1, we can compute b0, which is equal to the mean of y minus b1 times the mean of x. We've just solved for b1, and we know from the initial computations that the mean of y is equal to 77, and the mean of x is equal to 78. Therefore, b0 is equal to 77 minus 0.64 times 78, or about 26.77. By solving for b0 and b1, we have defined the regression equation. It is y prime equals 26.77 plus 0.64 times x. Before you actually use the regression equation, you should ask how well the equation fits the data. One way to assess fit is to compute r squared, the coefficient of determination. Recall that the coefficient of determination measures the proportion of variance in the dependent variable that is accounted for by the independent variable. So, when r squared is close to 0, regression tends to produce poor predictions. On the other hand, when r squared is much greater than 0, regression tends to produce good predictions. So let's compute the coefficient of determination. With simple linear regression, the easiest way to find the coefficient of determination is to first compute the correlation coefficient, which is equal to the sum of xy divided by the square root of the sum of x squared times the sum of y squared. We previously computed values for each term in this formula. The sum of xy is equal to 470, the sum of x squared is equal to 730, and the sum of y squared is equal to 630. So let's plug these values into the formula. The correlation between x and y is equal to 470 divided by the square root of 730 times 630, which is 0.69. Then the coefficient of determination is equal to the square of the correlation coefficient, which is 0.69 squared, or about 0.48. A coefficient of determination equal to 0.48 indicates that about 48% of the variation in the dependent variable can be explained by the independent variable. This is much greater than 0, which suggests that our regression equation will provide useful predictions. The formula that we just used to compute the coefficient of determination, r squared equals the square of the correlation coefficient, only works for simple linear regression. With other types of regression, a different formula would be required. Now that we've defined the regression equation and checked its fit, let's talk about how to use it. Probably the most common use of the regression equation is for prediction, predicting the dependent variable y when you know the independent variable x. In our example, the independent variable is the student's score on a math aptitude test. The dependent variable is the student's grade in statistics. Suppose the student made a 75 on her math test. What grade would we expect her to make in statistics? To answer this question, we turn to our regression equation. Y prime equals 26.77 plus 0.64 times x. If the student made a 75 on her math test, the regression equation predicts that her grade would be 26.77 plus 0.64 times 75, or about 74.8. When you use a regression equation for prediction, do not use values for the independent variable that are outside the range of values used to create the equation. This is called extrapolation, and it should be avoided. For example, here are the x and y values that we used in this example to create a regression equation. The x values range from 60 to 95. Therefore, we can use the x values between 60 and 95 in our regression equation to predict y scores. However, we should not use values outside that range, less than 60 or greater than 95. Let's review. Regression analysis is usually handled by a computer, and computations are hidden from view. In this lesson, we worked through a simple linear regression example by hand and showed all of the computations. You learned how to use raw data to compute mean scores, deviation scores, and summation terms that go into various formulas to produce regression outputs. We assigned values to b1, the slope of the regression equation, and to b0, the y-intercept. We used a regression equation to make a prediction, and we used the correlation between x and y to compute the coefficient of determination.
That's all, folks.